So this is the machine that we're going to be using today to perform our tensile test. The most important part of the machine is this part on the front here. So this is called the crosshead. This is the part which moves up and down to exert a force on our sample. As part of the crosshead, we have a force cell. Now this is a very accurate way of measuring forces being applied to the sample, up to, in this case, 5 kilonewton. And we also have the clamps in here which are going to hold our sample in place. Over here we have the tower which will move the crosshead up and down, and a control panel which allows us to manually reposition the crosshead. Now the only buttons that you'll need on the control panel today are the repositioning arrows here and the 0 button which resets the measurements. Over here we have our computer which is going to control our test and set all the parameters, how fast the test is run, any limits to where the test is going to end. And last of all, we have an emergency stop button down here. If anything goes wrong during the test, hit this as quick as you can. Everything stops, we can reset and go again. So we're now at the point where we want to load our sample up. The steps to do that: firstly, we want to get our sensor head in position using the fast repositioning buttons here with the double arrows. The reason we want to do that is obviously because we can reposition the head very quickly. The slow repositioning buttons we're going to use later, and as you can see, they only move the head very, very slowly. So we don't want to use them at this stage. What we don't want to do is to have our sample half loaded into the jaws and use the fast repositioning buttons, because what's going to happen there is you're going to put your sample in there, you'll try and bring it down to get it in the right spot, and you'll either overshoot, hit the sample on the bottom or the top here, your sample will bend and it will be no good for testing anymore. So the first thing we do is to get our clamps in approximately the right position, just by retesting on a regular basis until it's approximately the correct position. We then take one of our clamps, thread it through the hole in the top of the sample, check that the clamp is going to be around the right way. If the bottom of the clamp doesn't match up with the other end of the head, then you need to turn it over. And we screw that top half of the sample in. Now for the moment, we're going to screw that in quite loosely, so we're able to move the sample around, and that's to help us align this hole in the sample with the hole at the back of the clamp. So now we use our slow repositioning buttons, and looking through the clamp in this direction here, we should be able to line those two holes up. Getting those in approximately the right position. And then we take our second clamp and screw that in. Again, making sure that we've got it around the right way. You shouldn't need any huge amount of force. You can see I'm turning that very easily there without even really using the handles. If you have to wrench your clamp around very strongly, then it's a good chance that your sample is not aligned with the bottom hole very closely, and you've got your pin trying to go in on an angle. So you should, in that case, take the clamp out, try and reposition, and try again. As they're still going in quite easily, we can now tighten those up. So put them around to what I would call a good strong finger tight. You don't need to tighten them up excessively. Remember that you're going to have to get this sample out again at the end. One thing that you should be aware of is that as you tighten up the clamps to secure your sample, you may see an increase in the amount of force being measured. This can be monitored using the live force and extension measurements on the right-hand side of the screen. An increase in tension may indicate that your sample is very slightly misaligned. To fix this, we need to adjust the sample's position using the slow repositioning buttons on the bottom left of the console screen. Because in this case the sample is in tension, we need to move the crosshead very slightly downwards. Note that we don't use the tear button on the top right of the console window, which would simply reset both these measurements to 0 without actually changing the forces that are running through the sample. A force of 10 to 20 newtons is close enough to run the test. The last thing that you need to do before you start your test is to attach this piece of equipment here called an X10 Sumpter. Now this is a device that measures very, very accurately how far your sample has extended. Because it's quite an expensive piece of equipment and it's a little bit fiddly, your demonstrator will be the one to attach it to your sample. To do that, you simply disengage the holders there, attach it on in the appropriate position, and ensure that everything is lined up in the appropriate position. The last thing you do is to remember to release the safety pin. Push start to begin your test. A graph will appear and will track the progress of the test. You can zoom using the buttons on the top of the screen. At the beginning of the test, you should observe a linear graph. This is the elastic region and involves the stretching of bonds between atoms in the sample. Any deformation in this region is fully recoverable because the bonds are only stretched, not broken. The gradient of the slope gives us the elastic modulus of the material. At the end of the linear elastic region, we reach the yield stress of the material. At this point, atoms in the material begin to slip past each other. We're now in the region of plastic deformation. Bonds between the atoms are broken and new bonds may be formed as planes of atoms known as slip planes travel past each other. Because bonds are broken and reformed, any deformation that occurs in this region is permanent and the sample will not be able to recover its original dimensions. In the first part of the plastic region, deformation is evenly spread throughout the sample. However, at the point of maximal uniform elongation, some part of the sample will begin to form a neck. At this point, we've reached the ultimate tensile stress of the material, which is the top point of the graph. Once the neck has been formed, stress gets concentrated into a smaller cross-section, leading to further necking in that position, and this part of the sample will be the one that eventually breaks. Once your test is complete, right-click anywhere in the graph screen and select Data Point Export to save your data as a text file. This file can be opened as a spreadsheet for later analysis.